Here again, we have random variables x and y, and the random variable z is defined as their sum, but we assume x and y are independent. Okay, we will look at how to derive the distribution of z in this special case, because this is again um, a very frequently encountered case. X and y are independent and you need the distribution of their sum. Okay, this is a special case where we see a lot in research or in several applications. So it's worth our while to actually focus our attention to this special case. Now we have this result from this our previous discussion. Okay, therefore we just write this here again. But now you see, since x and y are independent, I can write this joint PDF in the product form. Okay, the PDF of x evaluated at this point, right, times the marginal PDF of y evaluated at y, integrated with respect to y. Now, this integral is a special integral. This is called the convolution integral. And in fact, this operation on the two functions, the PDF of x and the PDF of y, is called the convolution operation. Now, those of you who have studied signals and systems should be familiar with this. But if you are not, no worries. Just know that this is the convolution of two functions, f sub x and f sub y, and the definition is just this expression. Okay. In fact, we could have arrived at this expression not from this derivation, but from a different approach. Again, we will use conditioning and the law of total probability. We would like to find the PDF of z, which is the probability that x plus y is less than or equal to parameter z. So what I'm going to do is condition this event on the value of y, okay? And multiply this conditional probability with the PDF of y and integrate over all values of y, okay? Now here, when you fix the value of y, okay, then this event becomes random variable x less than or equal to z minus y. And z and y are parameters here. They are known values, okay? So this, you see, this probability is a probability only in terms of random variable x, whose value I can write easily, okay? This is nothing but the CDF of x evaluated at z minus y, okay? And then when you want to find the PDF of z, you just differentiate this integration with respect to z. Again, the differentiation can penetrate into this integral because the integral does not depend on z. Therefore, inside you have this function depending on z only. These do not depend on z. So differentiate that function with respect to z. And since this is the CDF of x, evaluates that z minus y, just apply the chain rule. First, differentiate the CDF of x, which gives you the PDF of x evaluated at this expression, times the derivative of this expression with respect to z, which is 1. So I don't write it here, times the PDF of y dy. So this is the exact same expression appearing here, and which is also defined as the correlation. Sorry, the convolution.